I'm Aaron Clausette. Today we have our very own Josh Grochow in our colloquium. Josh received his PhD in computer science in 2012 on work focused on symmetry and equivalence relations in classical and geometric complexity theory. He then took a postdoctoral fellowship in the Department of Computer Science at the University of Toronto, followed by an Omidyar fellowship at the prestigious Santa Fe Institute. Since 2016, he's been an assistant professor of computer science here at CU and is a core member of our Theory of Computer Science group. Josh's research focuses on computational complexity and complex systems and has produced a number of important results in the long-term program of understanding the famous P versus NP question and in understanding complex systems through the lens of computation. His work has appeared in prestigious venues including the JCM, SOTA, Sausage, ICALP, CCC, and the Bulletin of the American Mathematical Society. Today, he'll tell us about some of his work in a talk entitled, "Can we understand big systems from their small parts?" As a point of procedure, please hold your questions until the end, unless Josh asks for them. And please don't use the chat for questions. Thanks. And over to you, Josh.
All right. Thanks, Aaron, for the very generous introduction. And thanks, everyone, for coming. I'm glad to be able to tell everyone about some of this exciting work that I've been doing in the past few years. So I wanted to start with the big picture context of complex systems, which is sort of the umbrella under which all of my interests fall. And I don't usually like to give definitions of complex systems because in this context, almost any definition turns out to be too constraining. But for the purposes of this talk, we can think of them as systems composed of many interacting parts that produce some interesting and maybe unexpected global behavior from the interactions between the local behavior of all of these parts. And these show up all over the place. So you can think of, for example, the brain being composed of neurons, where each neuron, in comparison to the whole brain is a very simple part, but through their interactions, they produce some amazing things. Organisms being built out of cells, cities being built out of all of their constituents, the people, the vehicles, the construction, everything that's sort of happening in a city. This was the best picture I could come up with for an economy. It was a market of people and corporations trading goods in a market. Something like the internet, even an individual CPU, you can think of this way, where the transistors themselves are the simple components, and yet the CPU, even though we engineered it, right, it often produces unexpected behavior. And similarly with large software projects, right? Each individual module or function may still be very simple, but when a software project gets beyond a certain size, it often produces unexpected behavior, which is sometimes interesting and cool, and sometimes the source of many problems. So my work in general has sort of two aspects to it. One is about building theories, and the other is about developing algorithms. And when it comes to theory building, I like to think, what's the purpose here? The purpose is to provide some explanatory power, not just observe things in the world and take advantage of those correlations that we observe, but really understand what's happening and why. But beyond that, beyond just explaining what we see, I think the more exciting things about theory are when it provides useful but non-obvious analogies between different fields, where it really wasn't clear why these things should be related or even that they were related. And then, of course, there's always the happy two-way street between theory and application, where theory sort of contributes either suggesting fruitful solutions or directions to go in, and the applied side contributes, the applications, but also the sort of problems that are the meat that theory builds off of. And then when it comes to algorithm development, again, this is, a lot of it is about helping find patterns. When it comes to machine learning, people find sort of these very generic patterns. I mostly focus on more structured patterns where we know a little bit more what we're looking for. And so there's more structure for us to take advantage of. And yet at the same time, I like to pick problems where it's not so specific that, it only applies to one tiny thing, that it really generalizes across many different domains. And so there's a chance for it to be really widely applicable. All right, so with that context, I want to get to sort of the technical content of my talk, which is how do we understand complex systems? And there are, of course, many ways to do this, and I want to tell you about a few that I've been working on in the past few years. So one of the ways is people often describe complex systems or part of a complex system using networks. And the fact that we can almost always do this shouldn't be so surprising if we think of a network as just a way of describing pairwise relationships, right? You have entities that are nodes or vertices, and then you have edges between them that describe there's some sort of pairwise relationship between these nodes. This could be anything from physical connections like axons connecting neurons, roads, power lines, to trade, either physical or non-physical, like trade between cities, between individuals, or information trading as happens on social networks, or for example, when one paper cites another. It could be something more temporal, like activities, right? Acting in a movie together, writing a paper together. Or it could even be something incredibly abstract, like dependencies between variables in a differential equation, right? Where you have a node for each variable and you put an edge, you know, if dy dt depends on x. Or even dependencies between mathematical statements, where you have a node for each statement and you have an edge from A to B if A implies B. So it shouldn't be so surprising to us that networks are everywhere. But the problem is that most real-world networks are sort of too big to understand. Right? And so the question is, how do we do this? And the method I'm going to talk about today is by looking at their small subnetworks. I'm not saying this is the only method. There are certainly very many other very interesting and useful methods, but this is one that I've done a fair amount of work on. So the first thing you can ask is something like, well, how many triangles do you see in a network? And right off the bat, this actually tells you something. So for example, in social networks, we tend to see more triangles. And if you think, well, why? In social networks, what this is basically saying is, you know, if this is you and these are two of your friends, that they are likely to also be friends with one another. Oops. You can also ask how many squares, how many of this kind of graph, you know, how many of any given, whatever, 7-node subgraph you want to look at. And then when you find these, you want to understand why. What is this telling you about your big network? Right? But the nice thing is for the small networks that we're looking at, once we get the data from the big network, these small networks are usually much more interpretable. Okay, so to talk a little bit more technically about what's happening here, I want to actually go back to the graph isomorphism problem, which is a classical problem in algorithms and complexity, goes back at least to the 60s or 50s. And it's a fairly natural problem. It's I give you two graphs or networks, G and H, and the question is, can you relabel them, relabel the vertices of one to make them the same? So in this case, and you know, we often draw them by little pictures like these, but how we draw them doesn't matter. What matters is where the edges and the vertices are. So there's no vertex here. There's only vertices where I put the dots. The fact that these overlap is just an artifact of the drawing. And here you can see, let's see if I can do this in real time here. You can see that these are isomorphic if I take this and I just drag it over here, and now they look the same. So this is the question of graph isomorphism, and we want algorithms to do this. So we're going to have a little bit of audience participation here. So I had Chantel activate the yes/no button. So if you click on participants, you should be able to see the yes/no buttons. And this first one is like a softball here. So are these two graphs isomorphic? What do people think? Yes or no here? Yeah, so right, most people are saying no. Right, that's right. Does anyone want to venture a gander as to why? Like, what's the explanation? You want to actually prove this. And feel free
to have the same number of edges?
Sure, right, that's one way. They don't have the same number of edges, right? This one on the left has 3 edges, the one on the right has 2 edges. For these two, I mean, they're very small. There are very many ways to see this. Another way to see it would be to say, look at this node here. This node only has 1 edge adjacent to it, but every node in this other graph has 2 edges. And so no matter how you relabel things, there's always going to be a node over here with only 1 edge next to it. And over here, they're always going to have 2 edges. And this is what's called a local invariant, where I can look at just a small subgraph, in this case, a single node and the edges around it. And I can use those local invariants to try to distinguish graphs. Okay, now, what about these? Are these isomorphic? Now here, I'm not really asking you to sit down and do these. If you've seen this before, this is the famous Peterson graph in two of its famous drawings. And so they are indeed isomorphic. But if you didn't know that, how would you tell? Right? You might start looking at local invariants, like, well, how many edges are adjacent to each vertex? Turns out for all of them, it's 3. Right? Okay, well, that didn't help you distinguish them. And as you look at more and more local invariants, and they tend to always be the same for these two, you might start to think, well, maybe they are isomorphic. And now you have the problem of, how do I actually find an isomorphism? How do I map the vertices of one to the other to make them the same? Okay, so this is the graph isomorphism problem, and this will show up in how do we try and understand big networks by looking at their small subnetworks. Right, and so I want to come back to, though, graph isomorphism, I said people were looking at this in the 50s and 60s. That was long before the network science revolution and we had all this big data. Why were they looking at this? Right? I mean, sure, if you're a combinatorialist, it's sort of a natural enough problem, but, and they really were. So actually Cook and Levin, in their papers in the early 70s, when they first defined NP and NP completeness, they both asked explicitly about graph isomorphism in those papers. So one of the very interesting things, which we'll come back to when we get to tensors, is that graph isomorphism is universal for isomorphism of discrete structures, meaning any kind of structure you can describe where there's some finite set, and then there are some relations and functions on this set. And you have two of these things and you want to know, are they isomorphic? Any such structure you can convert into graphs in such a way that whether the two graphs are isomorphic tells you about whether your structures are isomorphic. So this includes things like partially ordered sets, k-ary relations, where a graph is normally a binary relation, algebraic structures, like if you've seen these finite groups, finite rings, topological structures like hypergraphs and simplicial complexes, and tons of other things. And so this says that it wasn't just sort of an odd mathematical curiosity, that this, it has some natural property that makes this a very useful problem for looking at. In sort of the same way as we say, like, why do we look at SAT? It's NP complete. Well, that's a good reason to look at it because it means better algorithms for SAT can be used for thousands of problems. There's sort of a similar thing happening here. Although it's not NP complete, it's a different kind of universality. The second reason is it's also interesting from the complexity viewpoint. So this is my kind of sketch of the world of P versus NP. P, you may recall, stands for the class of problems solvable in polynomial time, which is the sort of theoretical proxy for things that are efficiently solvable. And NP, the naming is unfortunate, but essentially what it captures is problems that can be solved by an exhaustive brute force guess and check search kind of algorithm. And then the NP complete problems we think of as up here, these are the hardest problems in NP in some precise sense. And really there are thousands of problems that people actually want to solve that are NP complete. There are also thousands of problems that people want to solve where we know how to solve them. Those are NP. But then we know from a theorem that if P is different from NP, which we think they are, that there has to be things in this middle region where they're in NP, but they're not NP complete and they're not NP. But the funny thing is, although we have thousands of things that we know are NP and thousands of things that we know are NP complete, there are only maybe 1 or 2 dozen natural problems that we think might be in this intermediate region. And graph isomorphism is one of them. This is actually, as I mentioned, Cook and Levin both asked about this in their original papers where they defined all of these concepts. This is the only problem from those papers, I believe, aside from P versus NP itself, that still remains open. They also asked about linear programming, primality, and a few other things that all got resolved in the intervening almost 50 years now. So it's also interesting from sort of the theoretical point of view. And then the last thing, which will bring us back to our main theme, is the applications. So there are some direct applications, like searching in a chemical database, right? If I tell you just the formula for a chemical, well, we know there's more structure to a chemical than that, and you can encode this structure as a graph. And if you come across a new chemical and you want to know if it's in some database, well, you have to go through and see, okay, is my graph isomorphic to some graph in this database? For those of you who aren't familiar, this is a very important chemical here. It's caffeine. It's also used in VLSI verification and a handful of other direct applications. But then there are a ton of indirect applications. because techniques that are used in graph isomorphism, like these local invariants I mentioned, are also useful for subgraph isomorphism. And this is exactly the problem of trying to study a network by looking at its small subnetworks. So subgraph isomorphism, you're also given two graphs, G and H, but now we're thinking of H as much smaller than G. And the question is, does G contain a subgraph isomorphic to H? Or how many copies of H does G have? This problem turns out is NP complete. And yet the techniques that we use for graph isomorphism, like local invariants, can still be used for this problem in practice, even though in the worst case, all the known algorithms are still exponential time. Okay, so now I want to tell you a little bit about like the theory of what can we learn about a graph by looking at its small subgraphs. Right? And we'll talk a little more about algorithms, and then we'll shift gears to tensors. So there's a famous conjecture going back to the 50s, late 50s, called the graph reconstruction conjecture. And this is the question of, if I give you all of the k-node subgraphs of G, where I don't tell you where they are in the graph, but I just tell you how many there are. So the analog would be how many triangles are there and how many paths of length 3 are there. And I do this up to some k. So this is dk of G. D is for deck, which is just the technical name for this set of graphs. You think of them as cards being drawn from a deck. And the question is, if I give you dk of G, what can you learn about G? And the conjecture, which seems fairly intuitive, is if I give you dn-1 of G, that uniquely determines the graph G. So what is this? This is telling you for every n-1 node subgraph, where G itself only has n nodes, I tell you all of those, and I tell you which of those are isomorphic to which other ones, right? So another way to say this is, I start with my graph, I remove one vertex, I take a snapshot, I put the vertex back, I remove the next vertex, I take a snapshot, I put it back. I give you all of those, and the conjecture is that this uniquely determines the graph up to isomorphism. It seems super intuitive, right? Like, I'm showing you so much of the graph, even by showing you a single n-1 vertex subgraph. Like, how could this not be true? And yet, this conjecture is open. It's known in certain special cases, but yeah, in general, it's still completely open. We do know things like there are pairs of graphs that are not isomorphic, but if you look at their n/2 size subgraphs, so only half the graph, they look the same, right? So if I count for each n/2 size subgraph, how many times does that appear? It's the same in G as it is in H for every possible n/2 size subgraph, and yet G and H are different. So, okay, we know, like, if you want to nail down G exactly, you need more than n/2. And the conjecture is that, it's somewhere between n/2 and n-1. But then very recently, Farhadian proved that almost all graphs are determined if you just look at the counts of their subgraphs of size 3 log n. So this is like a tiny fraction of the graph. It's a vanishingly small fraction of the graph, right? If you have, a million nodes, this is like looking at the 20 node subgraphs, or the 60 node subgraphs, I guess, right, out of a million node graph. And the almost all here means if I pick a graph uniformly at random, that this will be true. Okay. So this tells us, like, if you wanted to know your graph exactly, for most graphs, you actually can get away with relatively small subgraphs. Not super small, not size 3, but not size n/2, right? Only size log n. Okay. And what this tells you is that there's a potentially interesting regime, which is, well, what if you don't want to know your graph exactly? If your graph comes from real data, the chances that your real data are 100% accurate are almost nothing, right? So knowing your graph exactly is like too rigid because your data is not that accurate. But you want to know something about your graph. And so what this result is telling you is, well, look at counts of small subgraphs. Not too big, not 3 log n, but, small numbers, 3, 5, 7, 10, maybe even log n, right? But not log n. But there's this interesting range of small subgraphs where we might be able to access them algorithmically, which we'll come back to in a minute. And they may tell us a lot about our graph, but not so much that it's picking up, say, errors in our data. Okay, And this brings us to the concept of network motifs. So these were proposed in the early 2000s, sort of at the rise of network science, as small subgraphs that occur more frequently in your graph than you would expect at random. And there's a little star on the at random here because what this means is relative to some null model, where the null model shares some features of the actual graph you're looking at, but is somehow randomly constructed. So you might say, well, maybe I want to look at a random graph with the same number of nodes and edges as my graph, or a random graph with the same set of vertex degrees as my graph. And what they found, what they argued, they used a very brute force algorithm. So they only looked at subgraphs of size like up to 3, 4, maybe 5. And they found some interesting ones. So they were looking at genetic regulatory networks. And they said, oh, these subgraphs look pretty interesting, right? Like this one here on the left is a feed forward loop. And that says, if sort of this is a situation where the gene X upregulates the gene Y, which upregulates the gene Z, and the gene X also upregulates Z. Okay. And they said, oh, this little motif in my network actually serves a useful dynamic function. So just by looking at the structure of which genes affect which other genes, they could learn something about the dynamics. And they argued that these were sort of the building blocks of complex networks. Now, that claim itself, I think, is a little too strong, let's say, but motifs are still useful for learning things about networks. Okay, and now we come to the algorithms. How are we going to find these things? And I'm just going to focus on counting the subgraphs. The part about this random model, this random null model, I'm going to leave that. That's like, you can have a whole separate talk about random models and how to sample from them and which ones are good and not and so on. But let me just talk about the algorithms for actually counting the subgraphs. So in 2006 with Manolis Kallis, we had what was at the time the fastest algorithm for finding network motifs. And even today, the state-of-the-art algorithms due to Paredes and Ribeiro and Badiwe built off of the fundamental insight in our 2006 paper, which was to leverage symmetry breaking. And then very recently, just in the past year, I was working with Tarek Tomei, who is an undergrad now graduated from American University of Beirut, to improve these even further using some additional ideas from tree isomorphism. Basically because it turns out that in real world networks, there are a lot of trees. And so if you can speed up that part of your counting, that's a big win. Okay, so I told you a little bit about the theory of graphs and their subgraphs and what you can learn about graphs by looking at their subgraphs, and a very tiny bit about some of my contributions to algorithms. And now I want to shift gears to, oh, oops, I forgot what we can do with the algorithms now that we have them. Right, so one thing is, why do we want better algorithms? I mean, aside from people want better algorithms. Well, there are actually sort of good scientific reasons. So one is we can now look at much larger motifs. Instead of 5-node motifs, we can easily get up to 8 or 9-node motifs. And remember, this is exponential in the size of the motif, so that 5 or that 8 or 9 is appearing in the exponent. And so that's actually a pretty big win. We can also look at some motifs that are even much larger, 15, 20, 30 nodes. And now you can really start to ask new questions of your data. Like, how do smaller motifs fit together into larger motifs, right? When you could only get up to 5-node motifs, well, yeah, how do 3-node motifs fit together into 5-node motifs? There's only so much you can learn from that. Right? You can also ask things like, how do larger motifs cluster together, right? Once they get sufficiently large, they have to have some overlap. And how do they glue together to build up into your larger network? So you can really start to see how the structure of the larger network emerges from the structure of these small subgraphs. Okay, so now I want to shift gears to tensors. But before I do that, any questions about the graphs and networks stuff? And I guess you could either just use the raise hand feature or just unmute yourself and chime in. All right, well, as they say, I'll be here all week. All right, so let's shift gears and talk about tensors. So first, what are tensors? Well, tensors are, in some sense, just multi-dimensional arrays of numbers. So a one tensor or a one-dimensional array is just a vector, a two tensor is just a matrix, and a three tensor is like a 3D box of numbers, right? Where it's a 3D box of numbers. Okay. Now, you may notice there's a star on the R here, because it sort of depends on what your definition of is. And the reason for that is that it's not just a multi-dimensional array of numbers, right? I mean, you could take any set of numbers you want and put them in a 3D box and call it a tensor, but that doesn't make it a tensor. Just like if I had a list of numbers and I put them in a 2D array, we don't necessarily call that a matrix, right? Matrices are things where you can do certain things with them. They change in certain well-defined ways. For example, when you do a change of basis, right? You can multiply a matrix by a vector and that has meaning. Tensors are the same way. What really makes a multi-dimensional array of numbers a tensor is sort of how it transforms under change of basis, how it can be combined with other tensors or matrices or vectors. And so you'll often hear about tensors in machine learning, and often what they really mean is just multi-dimensional array of numbers, but there's no notion of change of basis or anything like that. Whereas for us, this whole notion of change of basis is actually going to be pretty crucial. So, okay, you can imagine, right, just as graphs are useful for describing complex systems, matrices are too, right? They're like graphs, but with numbers on the edges. But also tensors, right? If you want to describe something more than a pairwise relationship, say to every triple of vertices I, j, and k, you want to associate some weight, well, now suddenly you have a three tensor, right? For every I, j, and k, you have a number, you have a 3D box of numbers. Okay, so these will show up, and we want to sort of mimic the whole theory and algorithmic toolkit that I talked about for graphs, but now for tensors, right? Where we want to be able to look at their small subtensors, we want to ask, what is that telling us, and so on. But it turns out that it's more than just an analogy with graphs. Actually, tensors arise in studying graph isomorphism. And so I want to do a little bit of an aside to tell you that, and then we'll come back to tensors proper. Okay, so graph isomorphism, the state of the art, was this breakthrough result by Babai a few years ago, saying you could solve it in n to the log squared n time, where the previous best was like 2 to the root n. So this is, you know, if we replace log squared n by a constant, this would be polynomial time. So this is like much closer to polynomial time than 2 to the root n, which was the previous best, which was like exponential. It turns out that group isomorphism, where groups are a certain kind of algebra, is a special case of graph isomorphism. And the trivial algorithm for group isomorphism that leverages the algebraic structure was in n to the log n time. And so now these two are quite close, right? And if you want to improve further on graph isomorphism, say below n to the log n, well, you'll have to solve this as a special case. In particular, if you think graph isomorphism is in P, you first have to put group isomorphism in P, but we don't know that. N to the log n is the best we know for group isomorphism. Okay, and I've done quite a bit of work in this area, and to sort of show you where that work sits and also how tensors arise in this, I just want to tell you a tiny bit about how this problem breaks down. So it turns out that there are two special cases of group isomorphism which together combine to give you the general case. And they're called nilpotent radical and solvable. And solvable here doesn't mean you can solve the isomorphism problem. It goes back to the 1800s when they were trying to solve polynomial equations using square roots and division. But basically, if you could solve group isomorphism for these two special cases, whatever they are, that would solve the whole thing for you. Okay, and I'm not going to tell you what they are. That, you know, to tell you sort of what this whole picture is like a whole course in group theory. But again, I just want to give you the picture of sort of where things sit. So these cases break up further into other cases. Okay. And the idea is, you know, you start down here, can you solve the isomorphism problem for these? And you sort of work your way up. And in the past, so the things at the very bottom were solved in the 80s. And this one actually goes back to the classification of finite simple groups, which, if you haven't heard of it, is one of the biggest theorems in math. It's estimated to be something like 15,000 pages of journal articles spread across several hundred different articles. But once you have that theorem, this algorithm follows fairly readily. And then in the past roughly 10 years, there's actually been a fair amount of progress, some of which I've been involved in here. But the thing I want to draw your attention to is that both of these key cases rely on this case, the case of nilpotent groups. Okay, and this is where tensors show up. So just to recap our story here, group isomorphism, this algebraic, this problem from computational algebra, is a key bottleneck to further progress on algorithms for graph isomorphism. And in the context of group isomorphism, we're stuck at nilpotent groups. And one of the things that shows up in our work is that nilpotent group isomorphism is essentially the same as tensor isomorphism. So now, I don't really have to tell you about nilpotent groups. I can just tell you about tensors. And tensors are just boxes of numbers, which you're all now intimately familiar with. But at least they're not so unfamiliar. Okay, so this brings us to the tensor isomorphism problem. So let's start, right? We said one, tensors are vectors. So what is the isomorphism problem here? It's the question now of this change of basis. Just like in graphs, it was relabeling the vertices. In tensors, it's essentially relabeling your basis vectors, except now because we're in linear algebra land, you're allowed to take linear combinations. So for vectors, the question is, okay, I give you two vectors, t and t prime, and I ask, is there an invertible matrix A such that A times t, so this is just matrix vector multiplication, is equal to t prime? This problem is totally trivial because for any non-zero vectors t and t prime, there exists such a matrix. Okay. Now let's do matrices, two tensors. So now I have two matrices, t and t prime, right? They have rows and columns. And now I get to ask, well, I have rows and columns. I allow change of basis on the rows and change of basis on the columns. So I'm now asking, do there exist two matrices, A and B, invertible, such that if I left multiply by A and I right multiply by B, that transforms t to t prime. Okay, and this is exactly, A is doing row operations, B is doing column operations. So you may recall from linear algebra that if you can do both row operations and column operations separately, you can always make your matrix diagonal with ones and zeros on the diagonal, which means that I can do this kind of transformation if and only if t and t prime have the same rank. So for two tensor isomorphism is literally just computing matrix rank. Okay, it's harder than isomorphism of vectors, which was totally trivial, but this can still be done in cubic time, right? It's still in polynomial time. And then the question is, what about three tensors? What if I have a 3D box of numbers or higher, right? So just to be explicit, if I have a 3D box of numbers, I now have three directions that I can multiply by matrices. And I want to know, are there invertible matrices A, B, and C such that when I do that, I transform t into t prime? Okay. Now, this picture may not be very helpful, and neither is this equation, right? But I wanted to write it down so you could at least see it. Let me tell you how I actually think about this. Right? So the way I think about this is I actually take my tensor, which is a 3D box, and I slice it, let's say parallel to the screen. So S1 is going to be the front slice, S2 is behind that, S3 is behind that, and so on. Each slice is now just a matrix. Okay. And if I think of this first slice here sitting in the front of this box, what do A and B do? It's literally just left and right multiplying that matrix by A and B. So when I do this, but when I do this with A and B, I do it to all the slices at the same time. So if my slices are S1 up to SP, when I do A and B, I left multiply all of my slices by A, and I right multiply all of them by B. And then what is C doing? C is taking linear combinations of the slices, right? So you see here, like, let's just look at this one. This is a linear combination of all the slices, but with the same A and B in there. So what this means is, I don't actually care about the set of slices because I can take arbitrary linear combinations of them. What I care about is their span. So I can think of a tensor, a 3 tensor, as I give you a set of matrices, S1 up to SP, and what I care about is their span, all linear combinations of those matrices. Okay. And so if you look at this, what this is telling you is if I have two tensors and I think of their slices, the two tensors are isomorphic is the same as saying I can left and right multiply by A and B to make the span of this set equal to the span of this set, right? Where this span, the change of basis in these spans, is accounted for by C. Okay, so this is the three tensor isomorphism problem, and this is how I think of three tensors, because it's much easier for me to think of a set of matrices than it is for me to actually think of a 3D box, right? Because like I said, this picture, like if you're not thinking of this as a set of matrices, it's very unclear what this picture is telling you, right? But hopefully now that I've told you the secret of like, oh, just slice this box up and think of it as a list of matrices, now it's clearer, right? A is acting on the rows of the matrices, B is acting on the columns of the matrices, and C is mixing the matrices up with one another. Okay. So now we have the same thing that we started with for graphs, but now with tensors. So I'm drawing my tensors here as this is a pair of matrices. So I'm thinking of this as the two slices. So this is a 2 by 2 by 2 tensor where the front slice is 1, 1, 1, 0, and the back slice is 1, 0, 0, 1. And just like in the case of graphs, where I could ask, I showed you those two little graphs of size 3, and I said, are these isomorphic? And it was very easy for you to tell. Now here, these are like the smallest possible interesting tensors. And the question is, can you tell if these are isomorphic? It's much harder, right? And I'm not even gonna bother doing a poll. I mean, if you can see it immediately, good for you, come talk to me. But let me just walk you through it to give you a little bit more of a feel for this problem. So they are isomorphic, it turns out. And let me show you how. So that means I'm gonna take these two slices, S1 and S2, and I'm going to left and right multiply and take linear combinations of them to transform them into these slices. So the first thing I'm going to do is I'm going to diagonalize this matrix by left and right multiplying, not by an A and a B, but in this case by a particular A and its inverse. Because this, notice, is the identity matrix. So when I multiply on the left by A and on the right by A inverse, this one stays the identity matrix. So I can diagonalize this first matrix, keep the second one the identity matrix, and now it looks like this, where lambda is some eigenvalue. It happens to be a cube root of unity, but that's not super relevant. Okay, and now I can start taking linear combinations of these. So I'm gonna rescale this first one so that it looks like this. Okay. And now that it looks like this, well, now I'm gonna subtract this first one from this one to make this entry here 0. And then I'll take this one and I'll subtract a multiple of it back from here to make this entry 0. So this was my linear combination of my two slices. And then finally, I'll rescale this rightmost slice to turn that 1 minus lambda into a 1. And now these two are turned into these two. Okay. So this was literally the smallest possible example of tensor isomorphism. And already this is looking pretty non-trivial. And indeed, tensor isomorphism turns out to be much harder than graph isomorphism. It's not just in your heads, and it's not just because this is the first time you're seeing it. Okay, and then what if I ask you even about 3 by 3 by 3 tensors, right? I barely know where to get started on this one. I mean, I happen to know the answer because I built these, but if I just showed these to you, it's sort of anyone's guess what to do. Okay. So now I want to talk about what really is the relationship between tensor isomorphism and graph isomorphism, and how hard is tensor isomorphism, and what kind of things can we learn from it. So here is a very big diagram, which I don't expect you to absorb all of, but I expect you to absorb that it's big. There are some things I want to draw your attention to. So like here is graph isomorphism, here's group isomorphism. Here, this says P group iso. This is essentially the same as nilpotent groups, which was that special case that we mentioned before. And so this little part of this diagram is like that whole diagram I showed you before. Factoring integers, right? Traditionally hard problem on which much crypto is based is over here. And this reduces to, so it's no harder than several of these other problems here. And maybe some of you will be more interested in some of these problems than others. But the other thing to notice is that 3 tensor isomorphism is right here, and D tensor isomorphism is slightly above that. And sort of as you go up in this picture, problems get harder. And down here in this world, I had done some previous work. So, this G is me, these are me. But you'll notice like there are a lot of things that are really not connected here. Okay, and one of the things that I did with various collaborators is remedy that situation. So with Futorny and Sergeychuk, we proved that all of the problems listed on the previous page reduce to 3 tensor isomorphism. And this, another way to phrase this is exactly that tensor isomorphism is universal for linear algebraic structures. So remember at the beginning, we said graph isomorphism is universal for discrete structures where you have a finite set and some relations and functions. Well, now you have a finite vector space, a finite dimensional vector space, and you have some linear functions and some linear relations, or multilinear functions and multilinear relations. And it turns out that tensor isomorphism is universal for those. And so again, as with graph isomorphism, this says this is not just like a problem we picked out of thin air. This problem really is universal for a very natural class of structures that arise all over the place. So that was the first thing. And then we also went the other way. So with Yoming Chow, we showed the opposite, which is that 3 tensor isomorphism in turn reduces to all of those other problems in that picture, meaning they're all universal. So our picture used to look like this, and after those 2 papers, it now looks like this. And the key things to notice here, so first of all, everything in these dotted boxes, those are all now equivalent to one another, and they're all now universal for linear algebraic structures. So that's sort of a massive simplification, right? We had this, what seemed like a wild world of all these things, some of which reduced to some other things, and some of which didn't, and we didn't know, and it turns out they're all equivalent. Including, by the way, D tensor isomorphism reducing to 3 tensor isomorphism, if you follow sort of this path here. Okay. Right, so this was sort of our big theoretical breakthrough in the complexity of 3 tensor isomorphism in the past couple years. And actually, you know, this is a large enough class of problems that we actually got to name a new complexity class. So for graph isomorphism, there's a class called GI, which is the problems that reduce to graph isomorphism. And people talk about a problem being GI complete, meaning it's equivalent to graph isomorphism. We got to do the same for tensor isomorphism. So there's a great website called the Complexity Zoo, which lists your favorite complexity classes like P and NP, but also many more. So you see there's one for, I think, literally every letter of the alphabet. And the total number here is something like 500 or 600 classes here. And we, like our class, tensor isomorphism, got added to this zoo. So I don't know, that was kind of fun. Now, of course, this is a wiki, so like anyone can edit it. But even aside from that, you know, we really did feel like this is a very broad class of universal problems. And so as with graph isomorphism, it really deserves a name, right? And to sort of fit into this zoo of complexity classes. All right, let me see, how am I doing? All right, I'm gonna skip that slide. So there is one other sort of interesting thing that comes out of this, which we didn't really see for graphs. So there's a phenomena that many of you may be familiar with, or maybe this is reminding you of your theory of computation course that you took way back when, that there's this threshold between 2 and 3. So 2 sat is in P, 3 sat is NP complete, 2 coloring is in P, 3 coloring is NP complete, bipartite matching is in P, 3D matching is NP complete, and there are probably many dozens, if not hundreds of problems where there's some natural parameter, and when it's 2, the problem is in P, and when it's 3 or more, the problem is NP complete. Okay, and for tensors, we also saw this with 2 and 3. 2 tensor isomorphism was in P, that was just matrix rank. And 3 tensor isomorphism was universal for linear algebraic structures. But actually, it's not NP complete, or we have good reason to believe it's not NP complete in the same way we do for graph isomorphism. And so here we see this very interesting thing of, you see this same jump to universality from 2 to 3, but it's not about NP completeness. And so the question is, like, what is going on here, right? Is there some broader notion of universality that encompasses both what we see for tensors and the notion of NP completeness that sort of explains all of these? Like, why is the jump from 2 to 3 in all of these, even though In one case, it's about NP completeness. In another case, it's about linear algebraic isomorphism problems that are not NP complete. So anyways, I think this is sort of a very interesting thing. I have no idea how to get started on this, but it's like, I don't know, I hadn't seen this phenomenon outside the context of NP completeness before, and now we have, and that suddenly makes it much more interesting, I think. Okay, so in my last few minutes, I want to come back to algorithms for tensor isomorphism and for looking at small subtensors. So one question is, unlike graphs, there's a question of, for graphs, when you wanted to look at 3-node subgraphs, well, testing if 2 3-node subgraphs are isomorphic to one another so I can count them, that's easy. For tensors, it's not even clear that that's easy, right? And so this is sort of our first question. Our big goal in the long run is if I have tensors over, say, the integers mod q, I want to solve it in, say, q to the n time. So this would solve nilpotent group isomorphism in polynomial time in the size of the input. And so this seems like already a pretty ambitious goal, but one that's not maybe insanely out of reach. Right? So our first attempt is, if we're over a finite field, there are only finitely many n by n matrices A, B, and C that I can look at. So just look at all of them. So if I do this, this is like something like q to the 3n squared. That's the number of matrices. And then I have a polynomial factor here just because there's some multiplication that's going on, log q. This is like for arithmetic mod q. Okay, so 3n squared, even for small n, this is in the exponent. This is like way, way worse than q to the n. Okay. Our second attempt, though, if you look at this equation, what you realize is I could just enumerate 2 of these, brute force over 2 of these. And I can, once I've picked 2 of these to try, I can solve for C using linear algebra. Because if you look at our isomorphism equation here, imagine that T, T prime, A, and B are all given to you. Then this equation is linear in C. Right? So now I've reduced my q to the 3n squared to a q to the 2n squared. And the linear algebra gets absorbed in this polynomial factor here. Okay, that's pretty good. Turns out that you can naively continue this. So your first attempt was brute force all 3, your second attempt was brute force just 2. Turns out you can get away with brute forcing over just one of them. But now to solve for the other 2, you actually need a really non-trivial algorithm that was only developed in the last 20 years. And so you now get this down to q to the n squared times polynomial time. Right? And to see why this is so non-trivial, just look at this equation. If I fix t, a, and t prime, this is now quadratic equations in B and C. And general quadratic equations are NP complete. And so there's something special about the structure of these particular quadratic equations that makes it amenable to these very non-trivial algebraic algorithms. Okay. Now, this is still not great, right? This is still asymptotically, it's still q to the theta n squared, right? It seems like we haven't made progress. Practically, this is good. We've taken like the cube root of our runtime. But now remember, we want to look at small subtensors. So one nice thing is this only depends on one side length. So if one side length is small, I can choose to brute force over that side length, right? So if I'm looking at g by n tensors where g is small, this becomes q to the g squared polynomial in n and log q. And when g is small enough, that's polynomial time overall. So this is our first thing. This tells us now, if you wanted to look at the small subtensors, say the g by n subtensors, you can do it when g is small, right? You can do it efficiently. And now there's a second question is, well, how many are there? So for graphs, it was sort of clear, if I want to look at 3-node subgraphs of an n-node graph, there are at most n choose 3 of those, which is like n cubed, which is not so bad, right? But here it's linear algebra. And so there's a question of, well, how many of these things are there even when g is small? And it turns out that the answer is essentially q to the g times n minus g. So if g is small, say g is a constant, 5, 7, 10, this is q to the order n, right? And remember, that was our goal. So this is telling us that we now have sort of the algorithmic toolkit to look at these small subtensors. And now that we have the algorithmic toolkit, we can now ask about the theory. And this is all so new. I mean, you saw some of these results were just from last year, that the theory is mostly not developed yet. So you can do the same thing you did for graphs. You can say, I'm going to look at all G by N subtensors. You can ask, is every tensor determined up to isomorphism by looking at the n-1 by n subtensors? For small g, the analog of triangles and graphs, you can ask, what configurations of these tensor motifs can I see? There's some interesting work I did this past summer and ongoing with Michael Kliachman, who's a high school student in Chicago, and my PhD student, Michael Levitt. And then, as with the recent result of Farhadian for graphs, you can ask, well, what if I choose T randomly? What's the smallest G where T is determined by this? So these are all open. So the theory here is very exciting, sort of in rapid development, and it's like, it's a little bit like the Wild West. All right, so just to summarize, we talked about both networks and tensors, two different ways of describing different aspects of the structure of complex systems, and what we could, algorithms for studying their subnetworks and what we could learn from their subnetworks. So in the case of, or subtensors. So in the case of networks, right, we have state-of-the-art algorithms for counting these small subgraphs, and those are enabling us to study many new theoretical questions by looking at larger subgraphs. And in the case of tensors, well, we have some algorithmic progress on group isomorphism, right, which is sort of, if you remember this picture, it's sort of headed in the direction of general group isomorphism. I wouldn't say we're close, but the point is, the things that we've worked on are part of this larger program. We're stuck at nilpotent group isomorphism, which is secretly the same as tensor isomorphism. And we're really starting to develop, we have now sort of a basic algorithmic toolkit. We have some of the theory, like we have this universality result for tensor isomorphism. And then we're continuing to work on some of the many new and exciting open questions about tensors and their subtensors. All right, so I think that was everything I wanted to tell you, and I am happy to take your questions. Thanks.
Great, thank you. So we have a few minutes for questions, and I think we can use the raised hand function in order to sort of keep track of who's got questions pending. And Josh, I'll let you sort of manage what order you do them in.
Sure. Yeah, Brian.
Yeah, let's see. So in the tensor view, you have ij and k, and you have a connection between all three of them. Is one way you viewed it. Can you also view it as the entities just like I and j, but different kinds of connections being on the k-axis?
Yeah, absolutely. And people definitely do that. So people, even for graphs, people work with what are called multi-layer graphs or multi-layer networks, where you have a network with different kinds of edges. So not just putting weights on the edges, but actually different kinds, which maybe represent different relationships between the entities. And for each kind, you can think of that as one layer in your tensor. So if you have k different kinds of edges, and your graph is on n nodes, you get a k by n tensor. And people definitely do that, and they've actually used tensor methods to study these multi-layer networks and their properties in the same way that people use ordinary matrix methods to study ordinary networks. Yeah.
Thanks.
Yeah, Charlie.
So I'm curious, and this may be a bit long of a question, but I think you made a comment earlier where you were under the impression that 3 tensor isomorphism was not NP complete. And you seem to say that with a lot of confidence. I was not aware of that being the state. Could you speak a little bit more, or is it a little bit too hard to kind of, what's your feelings as to why this should be the case?
Right, so it's similar to graph isomorphism, where we know things like, if 3 tensor isomorphism is NP complete, then the polynomial hierarchy collapses. For graph isomorphism, there's also several other pieces of evidence why it's not NP complete, like counting the number of graph isomorphisms is the same as is equivalent, polytime equivalent to testing graphs for isomorphism. whereas we don't know of any NP-complete problems where that's true. And again, if it were always true, it would collapse the polynomial hierarchy. I don't think we know the same result. We sort of almost know the same result for tensors, but it's not quite polytime. But we do know, like as a theorem, if tensor isomorphism over finite fields is NP-complete, then the polynomial hierarchy collapses. Which, for those of you who aren't familiar, the polynomial hierarchy is a generalization of NP, and just like our intuition says that P is different from NP, our intuition actually says that the polynomial hierarchy does not collapse. It sort of continues going up and up and up. So this evidence is sort of like, it's almost like saying it's not NP complete unless P equals NP, but it's not quite that. Yeah.
That makes sense. Thank you.
Yeah. Other questions? Yeah, Aaron.
I had to go find my raised hand thing. So thinking back about the beginning of your talk, when you talked about the motif finding algorithms, that's a very practical application, somewhat sort of disconnected from the later complexity stuff. But it seems like there is a somewhat connection in the sense that, finding algorithms for finding motifs, some of them can be very expensive, especially if you want to run it on an enormous graph. Now, the biologists, of course, don't have really big graphs, but if you're looking at web scale graphs, then you're really talking about massive type things. So having worked on the other side, the complexity side of things, what is your view on how much faster those motif finding algorithms could get in the future?
Yeah, so it's actually an interesting question because, of course, it's an NP hard problem, and so we always expect that in the worst case, it's still going to be exponential time. But the whole thing about this, and actually, even for tensors, actually, although in practice tensor isomorphism seems much harder than graph isomorphism, we're also in the process of developing software that can actually do some of these things, looking at sort of tensor motifs. But coming back to your question about graphs, yeah, there's always this question of, okay, real world networks are not arbitrary. They're not completely arbitrary graphs that you're looking at. And so the question is, what's the structure there that you can take advantage of? And this was like this very recent algorithm I had with Tarek Tomei, the undergraduate, where we realized actually they have a lot of trees. And so that's something that we know how to take advantage of. And so in some sense, optimistically, I would say anytime you learn something new about the structure of real world networks that many of them have in common, you ought to be able to take advantage of that in some way for motif finding. And I don't think, based on, if you compare that to say clique finding, which is very advanced, I don't think it's unreasonable to think that you could easily look for sort of arbitrary 30 node motifs in the near future in things you could do on your laptop. Let's say, on the order of a few tens of thousands of nodes in the big graph. When you start talking about millions of nodes, now you're just limited by sheer numbers. Like even looking at all 5 node subgraphs in a million node graph, there are just too many of them, right? And so then you have to have some sort of sampling approach, which people also look at. And that actually, the sampling approach, of course, it's less accurate, but it can still give you insights into your networks, and that can then get much bigger even when your networks have millions of nodes. Yeah, Orion.
I apologize if this is ignorant, but I'm just curious. What's the fundamental difference between the group and the graph? You said there's the problem in understanding the group isomorphism was or the graph isomorphism is group isomorphism. So what's isn't it the same problem?
I see. No, sorry. I may have said something that was a little confusing at one point. So group isomorphism, I think one way to think about it that's accurate is it's a special algebraic subcase of graph isomorphism.
Right.
Yeah. And so there are certainly instances of graph isomorphism that seem totally unrelated to anything having to do with group isomorphism.
Mm-hmm.
But every instance of group isomorphism can be converted into a special case of graph isomorphism.
Okay.
Yeah. And part of the reason that it seems easier is that these groups, because they're algebraic, that algebra gives you a lot more structure. It's, yeah.
Thank you.
Yeah, Hamza.
Hey, can you hear me?
Yeah.
Yeah, perfect. So something that, like, to elaborate on what Orion just asked, could you shed some light on the relation between tensor isomorphism and nilpotent group isomorphism? And if there is a relation between them, like, what are the direct applications that we could see in the future?
Yeah, so I sort of hand-wavingly, they're essentially the same. And they're essentially the same, but up to a sort of difference of input. So what this means is you could solving tensor isomorphism in, say, p to the n time, if you're working over the integers mod p, is really equivalent to solving nilpotent group isomorphism in polynomial time. So there's this blow up of like p to the n time for tensors versus polynomial time for groups. But aside from that blow up, the problems are equivalent. And then, sorry, what was the second half of your question?
In terms of direct application. So if we do find a good algorithm to, solve tensor isomorphism, how would it impact the direct application of graph or group isomorphism?
Right. So if you find a good algorithm for tensor isomorphism, it would be solving these cases of nilpotent group isomorphism, which we think are the hardest cases. And those, I mean, even in practice, that's a hard problem where like, people use computer algebra systems. And if you're studying some conjecture or you're doing some topology or whatever, and these groups show up and you need to test, is your group isomorphic to some other, say, well-known group? Once the groups are even moderately sized, the current algorithms can't handle it. And so if you really had a good algorithm for tensor isomorphism, that really, really potentially extends the reach of those kinds of applications of computer algebra systems.
Got it. Thank you so much.
Yeah.
Okay, let's end there. Thank you, everyone. And thank you, Josh, for a really interesting colloquium. And we'll see you all next time.
Thanks, everyone.